One of the most powerful diagnostic tools of the past 30 years has been the availability of body scans to investigate medical conditions. Technologies such as PET and CT scans introduce radioactive tracers to record images of internal organs, the blood flow, and orthopedic conditions. These images have provided life-saving insights to diagnose specific conditions, as well as measuring the efficacy of ongoing treatment. The effect of radioactive tracers injected into the body has become a risk issue, and repeated scans have reached the current lifetime limits for radiation exposure on some patients. My name is Jim Conner. Welcome to Game Changer Silicon Valley. My guests are Anna Christensen, CEO, and Patrick Goodwill, CTO, both of Magnetic Insight. Anna and Patrick, welcome to the show. Let's start with an overview of the medical scanning technologies in use today and how Magnetic Insight is removing the radiation risk associated with diagnostic scans.
Thanks, Jim. Thanks for having us today. So medical imaging really has a quite impressive tool chest of imaging technologies. We have CT, PET, MRI, ultrasound, and all those modalities, all those technologies answer different questions. And many of those modalities were developed over 30 years ago, and we still actively use them now in the clinic and in research.
So on the technical side, the primary difference between these techniques is there's these anatomical techniques and there's molecular imaging techniques. So anatomical, we have CT, MRI, ultrasound, and what they fundamentally see is tissue. They see tissue, and surprisingly, live tissue, dead tissue, they look very similar. And so one of the fundamental differences between that technology and molecular imaging, which is, for example, nuclear medicine, PET, SPECT, and MPI, is we see function. We see something very different. We see much deeper, and we see how things are working and how, say, in MPI, how things are flowing through the body. In nuclear medicine, you can see locations for cancer, things like that. So they're very different.
So I have the impression, based on that the older, call it PET scan, is an image, period, at which you're looking for maybe a blockage or something obvious. And the MPI and the newer technologies are more of a movie, if I can use that.
If you're looking at the heart and say you're looking at PET and SPECT, you can see the different phases of the heart motion, and you can see whether parts of your heart are working properly or not. So there's some movies in there as well. But what makes MPI very unique, and along with some of the newer technologies and say very fast CT, real-time MRI, is we see things moving in real time. For us, we can get images that happen every few seconds and see how blood flows into the brain, how blood is flowing through the body, and see how perfusion is happening in the body. So very much on that function side.
So are you a little more focused on the motion, meaning the blood flow and those types of things, and less on the, shall we say, the knee joint or the back or something like that?
Right. So we're able to actually see nanoparticles moving through the blood, and we're able to quantitate what's happening in real time. And this gives doctors a lot of information on the integrity of the blood vessels and any potential issues that may or have occurred.
I take it there are no other technologies doing this. Is that correct, just to be accurate?
There are some similar technologies, but nothing that really goes as intense as molecular in molecular imaging, and MPI, which is magnetic particle imaging, gives us a whole other breadth of information, and of course without the radiation, such as in CT.
That's a good point. Let's talk a little about this radiation issue, which is becoming very visible and very controversial, I think. Maybe I can ask you, Patrick, as I understand the earlier technologies, PET and CT scan, you're injected with, or you breathe, or you give a pill to have something that is a radioactive tracer, meaning it's giving off particles. It's an energetic particle thing that's putting out electrons, I suppose, or neutrons or something, and then you take an image of that radiation.
So there's a let's unpack that a little bit. All right.
Yeah.
So
I need a correction of that.
So on CT is you're taking a picture. You're taking an X-ray picture, and so there's not an injectable radioactive tracer, but what you're using to take that picture is radioactive. So the act of taking that picture, you're sending X-rays through your body, and that has implications. So it can cause it does cause your DNA to break apart. Now your body can repair a lot of DNA, but it doesn't always repair all of it. And so with every bit of radiation that you get, you increase your chance of cancer. And nuclear medicine, well, this is the one that you inject a radioactive tracer. And you inject, nuclear medicine, you inject PET and SPECT, they're different sort of tracers, and they both cause exactly the same thing as taking an X-ray picture. And oftentimes, PET and SPECT are also added together with a CT scan, so it increases the radiation even more. And so there's a lot of exposure that's happening with these techniques.
I did a little reading, trying to prepare and be halfway conversational, and I got the impression that this radiation is accumulative, and then other articles said no, the body passes it out, it breaks it down, and metabolizes it, and you put it out through your urine, what have you.
So the actual tracer, so the radioisotopic tracer gets broken down and cleared through the body, but the accumulative ionizing radiation, whether it's coming from CT, an external source, or internally from a tracer, is cumulative. So during your life, every time you have a CT scan or PET SPECT, the ionizing radiation adds up. So potentially, if you can see young adults or even children who have to go through many rounds of CT or nuclear medicine, some of them hit their life dosage very early on.
Is there a measure of some analogy you could give me or the audience about what is a dangerous level of accumulated radiation? Would it be perhaps getting an X-ray every week for a year? Might be an example.
So there's a definite limits on how much radiation that we can get. And an X-ray in itself is actually not that much. But a CT scan, for example, is equivalent to 50 chest X-rays. A PET scan is very similar. And so when we're looking at the tomographic PET, SPECT, CT, these are just very large radiation dosages. And if you get a couple CT scans, all of a sudden you just got 100 chest X-rays. That's not something that most people want to do. And it also matters on your time in life. So an older patient, it's not as much a worry because there's a lot of time, there's not that much time left in the relative term, and your body is changing much slower. For a younger patient, say someone like a child, that amount of radiation from a single chest X-ray can appreciably increase their chance of leukemia later in life. And so there's a lot of different aspects that are happening in the background, and we just really have to minimize how much radiation that we give people, just in case.
Yeah, it's kind of like if you have to have it, okay, but be aware of what your dosage is, and you might want to think about holding off for 4 or 5 years until the next time it happens, right?
Exactly.
And we're in a situation right now where there isn't any other option for patients to monitor disease or to diagnose disease other than to use these radiative approaches. And so that's why we're very excited about magnetic particle imaging.
So let's get to the heart of the matter then. Tell us about magnetic particle imaging. How did you find this? What was it an obvious need and there was a problem, or did you were doing some research and stumble across it? Maybe I'll let you start.
Go ahead.
So I'm fundamentally a gearhead.
That means scientist.
A
right?
scientist. I like to build
I'm
things.
really happy this is recorded then, because I call him that all the time.
And what happened was about 10 years ago, I went to grad school for, I guess, the second time, and I left my previous career designing chips at Intel. And I wanted to do something that is more impactful to greater society, and I wanted to do something in health. And so in 2004, I went to Berkeley and I started working on magnetic particle imaging. And at the time, someone had published just the first paper, and it was just the inkling of that maybe there's something there. And we've talked about the previous types of the existing types of medical imaging. There are 4 types, all right? Just keep that in mind. This is a 5th. So what it's doing, it's really increasing what doctors will have available to them to improve diagnoses. And so back in 2004, we started working on this, and over the next 10 years, and a lot of pain and struggle to get funding, to convince people that we can do this, to actually get it to work. I mean, these early papers, they just don't work. So we've been able to bring it to this point where we have it working. We have it functioning. We have it working in small animals, and we have this path to get to the clinic. And that's when we realized, I think it's time. It's time to bring another university. And that's when we connected,
right.
and I can take it from there.
Yeah, I mean, so the point to where they got their technology, and I met Patrick, they were able to answer questions that scientists have had a hard time answering with current technologies. And so I used to wear a white jacket and was in neuroscience and cell biology, and then for the last 17 years on the commercial end of imaging and diagnostics. And when I met Patrick, it was immediate that the technology, magnetic particle imaging, was answering major challenges that we weren't able to answer with current technologies. And the direction that current technologies, meaning CT, MRI, and PET SPECT, were going was more in a Swiss Army knife. Let's put them all together and combine these modalities together, not really to answer more questions, but just to make the workflow better. But when I learned about magnetic particle imaging, this was just a complete disruption in the imaging community. This is able to take technology beyond to where it is right now, to the technology that was developed 30 years ago, and start answering questions about vascular function, where stem cells are going, immune cell therapy. And these have been major challenges that we've seen.
It sounds like you're going to focus right away on areas of unknown information or unknown working processes. Is that correct? Maybe the brain, the blood flow in the brain?
Absolutely, absolutely.
So we might see some dramatic breakthroughs as you start to deploy this. Is that correct?
That's our goal. That's our goal. I mean, our goal here is to really start diagnosing pathologies much earlier on, to be able to look at susceptibility of diseases, and to be able to monitor diseases without worrying about radiation trade-offs later down the line, and give doctors the tools for that.
Right. So you're going to not necessarily display CT or PET. You're going to add to the imaging availability or the alternatives for imaging in a we'll say perhaps safer way, we think, in a more dramatic and dynamic way, meaning real-time feedback. So you're more of I don't want to say disruptive, you're more of a step out of what is there today. You're not looking to displace all these machines right away. You're going to go prove that you have something completely different and better.
Enablement.
Yeah. Enablement.
Absolutely.
I love it. So,
Yes.
What's going on now? I know you're in arrays, but you're starting to deploy this. You have it over
Right.
at Berkeley,
Right.
and you've got I saw on your webpage a pipeline, or somewhere I saw this pipeline of companies waiting to get these machines going.
Right, right. So we do. There's a lot of interest with magnetic particle imaging. We've just started to come out and talk to the rest of the world about what we can do, and showing them data of what we can enable in their labs, and the response has been overwhelming. So we do have a nice sized pipeline that will slowly roll out in the next few years to research labs. We'll be entering quite a big consortium that will release soon enough, that will combine not only the bench the bench side perspective, the research perspective of magnetic particle imaging, but also the translation into clinical imaging. And that is a very exciting endeavor for us, to have a team on both ends of the spectrum, both research and the clinic, and not only answering questions for research purposes, but also looking at translational imaging protocols, so we can get a really quick kickstart in the clinic.
So if, there's so many areas out there, aging diseases, Alzheimer's, all these things, I'm particularly aware of those things, because we get a little older. And where do you think this will be focused first? Will it be on young people, middle-aged people, or just common diseases within a demographic?
Our introduction to the market, first we're starting with the preclinical, but we're using this preclinical market as a way to prove our different clinical paths. So our first clinical path, for technical reasons, is we're going to be going to the brain. And we can scale this small animal scanner directly into a human head-sized version. Now, as we get to the full body, the technology changes a little bit, and we can scale it there, but we want to take baby steps. So we're going to go straight to the brain, and there's some very compelling applications there, whether it be brain perfusion, cancer imaging, and tracking immune cells into the brain. A lot of these brain diseases are diseases of inflammation, diseases of how your body is reacting to something that is not going right. And so we should be able to see those.
And then you could probably treat them as a preventative or an early detection system?
So we can diagnose them earlier. That means the earlier we diagnose things, perhaps the better we can treat them. Yeah. And the better we treat them, of course, the patients, this is really what they've always wanted.
Yeah. Go ahead.
No, just to add on to Patrick, is one of the main challenges now in neurovascular disease is to be able to actually monitor the patients post-event. Things happen in the brain and especially in the neurovascular where you really need to monitor what's going on, such as vasospasm, post-hemorrhagic stroke issues. And we just do not have that available technology that's safe enough so we can monitor these patients. And so assessing patients long-term is good.
That's a great point, because all these great treatments are coming out, but they tend to do a 2 to 5 year study, and they just see, did they die or did they live, and that's kind of the metrics, and how long did they live. And having this monitoring of the brain and internal functions from a real time has got to be a tremendous breakthrough for all this area, both treatment of disease, but also monitoring and showing the efficacy of the various new treatments that are coming out.
Absolutely.
If people want to follow up with the company, contact you, know more about this, what is the website, what should they do, how do they get in, how do they get more information?
Yes, you can absolutely get online and go to magneticinsight.com, and we keep the website up to date and share with everyone where we are, what is the newest things that are happening with the company and developments. And absolutely, we have webinars to talk about the technology that you can go through. And
that's great.
Yeah.
That's great. Anything we should look for from a technical perspective from you, your group, Patrick?
Well, I would actually emphasize people should take a look at the webinars. We have I think it's about an hour and a half now. An hour and a half of content that people are very welcome to take a look at. It goes through the technology pretty deep, and it also goes through a lot of the applications with examples in the preclinical and where it could possibly go in the clinical sense.
That's great. Well, I have to thank both of you so much, because I've learned a lot. I read a little bit about the technology. Fascinating story. Could be a tremendous game changer, breakthrough for treatment, diagnostics, as well as ongoing results and efficacy. So I wish you every success. I hope to see you guys out there in the public media. I hope maybe this little show can be your entry into the public media and get you more attention. So thanks so much for coming by, and we look forward to keeping in touch with you.
thank you, Jim.
Thank you.
Thank you for joining us for this week's episode of Game Changer Silicon Valley. Each week we'll address an area of innovation that may emerge as a game changer of tomorrow. You can follow us on our Facebook page or subscribe to our YouTube channel. We'll be right back with our second segment of tonight's show.